Okay, this group is Newton's law of cooling, and we're going to do time of death. This is like real world. Everything we do here is real world stuff, but this really gets used all the time. You've all seen on CSI when they say, "Oh, this body's been based on liver temperature. This body's been dead for 7 hours." They're using Newton's law of cooling to do that, and they have to make assumptions. Remember, here's Newton's law of cooling, where capital T is your temperature, and we're going to say for us degrees Fahrenheit at time T. T is measured in hours. A is our ambient air temperature, and K is our constant of proportionality here. It's related to the heat capacities of air and skin and so forth. And we're going to use this value, negative 0.223. Okay, we're going to look at a few different scenarios. So here's our our setup. Say a body was found at 8 a.m. We want to work backwards and see what time the person was killed based on three different scenarios. And with this project, this is the one you get to be the most creative with. I want you to pretend like you're a detective and make up a scenario. Make up a whole, well, we know if the person was killed before 2 a.m., it had to have been Dave because he was the only one around. And if the person was killed between these times, it must have been Joe because only he was around, that kind of thing. Like, make up a whole game out of this, like a game of Clue. And like, you'll solve all the math first and then work backwards and make up the game and actually solve the crime, figure out who did it based on what we figure out. So we're going to have three different scenarios. Either the body was outside the whole time with constant air temperature. Let's say the body was indoors, constant A at let's say 70 degrees Fahrenheit. Scenario two, so that would be one, two, let's say outside where A is a function of time now. It's going to be increasing linearly. So maybe A of T started pretty chilly and has been rising. So maybe was 30 degrees, but it's been going up by 10 degrees per hour. And then three, maybe the body was in something that was climate controlled, but the air has been oscillating, some wavering temperature, maybe like in a greenhouse or something where like you get to make up a scenario here, but a greenhouse where A of T is 70 degrees, but it goes up and down by 10 degrees. You know, it oscillates around 70, goes up to 80 and down to 60. And let's see, we want cosine of omega t. Let's say our period is every hour. So this should be 2 pi over 24 t. So pi over 12 right there. Let me think about this and make sure this is right. Yeah, here's our period 20. Oh, no, no, that would be every 24 hours. We want it every hour. Oh, so just one there. So 2 pi t. So I want to make sure I got my units right here. Yeah, this will work. Okay, so the temperature, the ambient air temperature is 70 degrees, but it's going to oscillate above and below 70 up to 80 and down to 60. And again, you're going to make up some scenario where we found the body, but we're not sure where it's been stored for the last few hours. Has it been sitting outside the entire time, or was it in this building that we found it next to, and then somebody just moved it outside? Or maybe it was over in this greenhouse across the way and somebody just moved it outside. Okay, we know in all three cases, T at zero, this is time of death here, TOD is about 98.6 degrees. That's actually a myth. Average body temperature is not 98.6. It's actually a little lower than that. And like if you want to, you can Google and find what it really is and use that, or you can just use this, either way. But let's say we use this. So you're going to solve each of these individual cases, figure out, so you'll get T of T equals some function here. Solve in each case when T equals, let's call it T1, equals what temperature did we find the body at? Oh, we haven't said yet. Let's say 82 degrees Fahrenheit. Yeah, I think this will work. So figure out how long that took, and then you go to work backwards from that to figure out the time of death. So remember, time one corresponds to, it doesn't equal 8 a.m., but is at 8 a.m. So if I end up with T1 equals 3.5, then I know the person died 3.5 hours before 8 a.m., which would be like what, 4:30? So you have to work backwards and find the time of death. So find all three possible times of death. Should I put T's of D and solve the case? Okay, now solving each of these. Like let's specifically, because a lot of times groups will struggle with solving the DE. Let's just write out what you would do in, say, case three. So, for example, case three, I've got dt equals k t minus a, where a is now a function. So k t minus, and then in parentheses, what do we have? 70 plus 10 cosine of 2 pi t. So I've got a couple of different levels of distribution here. I have to distribute this minus and distribute this k. So this would be kt minus 70k minus 10k cosine of 2 pi t. This is linear first order homogeneous. We got a couple of different ways we can solve it. We could solve it using an integrating factor, but I think that's going to be the hardest way. Is it separable? Yeah, it is separable, but that would be a nightmare. You do not want to solve this as a separable because this whole thing would come down on the bottom and then you would have a dt here. This would all be your denominator. That would be awful. No, I would say solve this as first order non-homogeneous. So do t prime minus kt equals all this stuff. So you would solve the homogeneous version first, Set this equal to 0. Get your characteristic polynomial. It's going to be a linear equation. You're only going to have one constant of integration. Then, like, just do it. Equals 0, you get lambda minus k equals 0, you get lambda equals k. So my complementary solution will be C1 e to the kt. Now I have to find my particular solution. So TP, now it has to have this form. It needs to have a linear factor, some a, or no, that's a constant. There's no t in there. So it's some constant plus I need to have sines and cosines. So some b times a cosine 2 pi t plus some c times a sine 2 pi t. And you'll solve for a, b, and c. Take the first derivative. It's a non-homogeneous equation. Solve it using undetermined coefficients. Find your coefficients, stick it all together. Going to be a similar game for scenario 2, only now your particular solution will just be a linear a t plus b. And for the regular, like we've solved Newton's law of cooling. So here with a constant a, you already know what your solution is going to look like. It's one of the first lecture videos we did. So go back and look at that, or just solve it. Okay. So in the paper, you're going to go through all these details. You're going to show all the steps. You're going to, again, you get to be creative. You get to make up some CSI kind of case. Have three different suspects, and at the end, solve the murder. We know because remember, you're going to have three different times of death. Now, sometimes I should point this out here. In this third scenario, because the temperature is going up and down, some weird stuff can happen because all the temperatures are less than 82. I do think we will have a solution, but occasionally when we're doing this project, I might make up numbers here where this never gets down to 82, which would just eliminate this possibility. If that happens, you would just say, oh, well, we know the body wasn't stored in the greenhouse because that body would never get down to 82. But I don't think that's going to happen here because these temperatures are all less than 82. So in each one, find a time of death, create scenarios explaining why, oh, it must have been Bob that did it because he was the only one in the area at that time, that kind of thing. Okay, so you type all that up. It'll all be beautiful. Let me show you the best way to type up math. I highly recommend using Google Docs. Then you can share, everybody can work on the document at once. It's a live document. You're all probably engineering majors. You're going to have to learn LaTeX at some point. So I highly recommend adding on this extension called Auto LaTeX Equations. LaTeX is mathematical typing software. So we're just going to type all of our math. Please don't use like equation editor in Microsoft Word. It's terrible. It even tells us here in the directions, all of my math needs to be embedded in these dollar signs. So here our DE is, like if I want to do a fraction, I do frac dt dt. You can see how it works there. The numerator is in brackets, the denominator is in brackets. And equals like k t minus a. Say how we're typing this. Put my dollar signs on both sides, hit render, and it's going to give me a nice, beautiful equation. You may have to learn a little bit of LaTeX. You may have to Google, how do I type this in LaTeX? Just Google it. There are plenty of resources out there. So you'll type up all the math. You can potentially just type the entire paper and hit render at the end. It'll go through and render all your equations. I don't recommend that because you're going to make mistakes. Type a little bit, 3 or 4 equations, hit render, keep going. If you do make a mistake, just highlight your equation, hit back, the left arrow key, get right before the equation, hit de-render, and you can go in and edit. So type up the entire paper first, then we'll create the slideshow. So remember, everybody has to present. You're going to record a video of you presenting your chunk. The entire group is responsible for the entire project. So I know how you guys work. You might think, oh, well, I agreed in our group meeting that I'm going to do number 2. And you know number 2 is perfect, and you say, forget about everybody else. I did number 2. That's not the way I grade. I'm grading the entire project. So if you do split up the work like that, you still have to double check everybody else. Everybody is graded. Your name's on the project. You're responsible for the whole thing. So double check each other. When it gets typed up, it should look consistent. Do not split up the work and have one person type a section and another person type a different section unless those look the same. It shouldn't look like 3 different people or 4 different people typed it up. Double check each other, type up everything here. My recommendation, type up the whole thing first, then build your slideshow. Now, I know you guys like all your fancy transitions and animations and backgrounds. Like, I could not care less about any of that. I'm perfectly fine if your whole presentation is a white background and black text. I don't need anything else. Like, I will not take points off if you don't have any backgrounds or fancy animations. If you want them, sure, but I wouldn't spend too much time working. What I want to see here in the presentation itself are all the major points. Your entire presentation is 10 to 15 minutes long. I would rather you go 9.5 minutes than 15.5 minutes. I'd rather you be under than over. Like, you want to shoot for, like, say, I don't know, 11, 12 minutes. Absolutely do not go over 15. I will take points off if you go over 15. If you're ever invited to a conference and they tell you you have 15 minutes and you go 16, they'll never invite you back. It's incredibly rude. You're bored with me talking right now. Nobody wants to listen to this for 16 minutes. Keep it under 15. Everybody has to present. My number one rule, do not read to your audience. You're going to have a bunch of text in your paper. Do not copy big giant blocks, paragraphs of text and put it in your slideshow. You should never have too much information on the screen at one time because people won't listen to you. They'll be trying to read all the words on the screen. And absolutely do not put a bunch of words up on the screen and then read it to me. I learned how to read in elementary school. Do not read to me. Just as importantly, a lot of times they'll just have the right amount of information on the screen, but you can tell they're just reading the paper. They have it printed off and they're just like, at 9 a.m., a body was found behind the Walmart on 7th Street. And then, like, for like 6 minutes straight, just this monotone voice of somebody reading. That is so boring. That is the surest way to lose points on this project. Do not read to your audience. Do not read math to your audience. So you're going to have like a bunch of math here, like what I was doing here. dt equals kt minus a parentheses dt equals k parentheses t minus parentheses 70 plus. That is so boring. Here's our dE. We know a is this 70 plus cosine. We're going to distribute our minus. We're going to solve the homogeneous version first. Here's our characteristic polynomial. Here's what we get for a complementary solution. You got a mouse. Whoever's talking should have control of the mouse and use that mouse to point to stuff. Do not read all the math to us. Go over all the important features and just point to stuff. Make sure you have graphs for every one of these. Absolutely, you must have a graph for each scenario. And you must talk about the graph. The entire point of having the graph, write a sentence or two. We can see from the graph that the body reached 82 degrees after 6 hours. Therefore, the person was killed at 2 a.m. Okay, so you've typed up your paper. Now you're going to build your slideshow. Again, I recommend typing the entire paper first. Then you can just come here, click on your, say, an equation, come over here, Control V, Control C. I can move it around. I can resize it. Don't reinvent the wheel. Type up all the math once and then copy and paste it into the slideshow. Don't read to your audience. Okay, I think that's a good place to stop here.